This lecture begins wave kinematics. This lecture is specific to Physics AB and Honors Physics AB. Okay, describing the propagation of a wave, that's what wave kinematics is all about. Wave kinematics is concerned with developing the following type of function. Okay, we define two coordinate axes here, the x direction and the y direction. The x direction specifically means, by definition, that we're talking about the direction of propagation. Okay, and then the y-axis, perpendicular to that, represents the disturbance of, or rather displacement, of the medium from its equilibrium position. Now this could be either transverse or longitudinal. So for example, for a single transverse wave pulse, this is just the easiest way to picture it, the y direction then is just simply perpendicular to a spring, for example, that is laid out along the x-axis. So for a single transverse wave pulse, basically wave kinematics would be concerned with describing the following type of function. So right here, for example, we'll say is a single transverse wave pulse like so, which propagates along the x-axis with a speed v. And then the function that is necessary to describe its propagation has the following form. This expression right here. Now, developing this function for a single transverse wave pulse, or a longitudinal pulse for that matter, is actually quite difficult to do, and it's beyond the scope of this course. So for that reason, what we're going to do is develop this function then for the simplest possible wave to describe mathematically. The simplest possible wave to describe mathematically is called a simple periodic wave. For a simple periodic wave, all sections of the medium are in simple harmonic motion, and all of the individual simple harmonic oscillators are slightly out of phase with respect to their adjacent counterparts. So we will develop this expression for a simple periodic wave. Once again, for a simple periodic wave, all sections of the medium are in simple harmonic motion. And all of the simple harmonic oscillators are slightly out of phase with respect to each other. So then therefore, what would such a wave look like? Well, imagine holding onto the spring, for example, and then oscillating your hand back and forth like so, such that you then set the entire medium into simple harmonic motion. But the energy that you use in doing work propagates then through the medium, resulting in a wave form where if you took a picture of it, for example, at some moment in time, just looks like this. Okay, let me go ahead and do some erasing. And then here is that wave. Like so, propagating in this direction, for example, with a speed v. As we'll see, mathematically describing the propagation of such a wave is rather straightforward. Before we do, however, there are some definitions and some terms to go over here in the context of a simple periodic wave. Mathematically, there's no difference between the tops and bottoms of the wave, if you will, but we do give them different names. The tops of the waves are referred to as crests, and the bottoms are referred to as troughs. Okay, now as long as the wave is a simple periodic wave, then the distance from crest to crest, which is the same as the distance from trough to trough, never changes. That distance, for example, say right here on the diagram, is referred to as the wavelength. The wavelength is always described by the Greek letter lambda. And now let's say, for example, that there's a person here, like so, just watching the waves go by. Let's say that the person counts the number of waves, the number of wavelengths that goes by per second. In doing so, that means that the person, the observer, is measuring the frequency. So the frequency f is the number of waves per second. Once again, anything that is in terms of per second is referred to as hertz. And then, of course, we have the period. The period would be the time necessary for one wave to go by. As you'll see, mathematically, this is the same as the period of the simple harmonic motion associated with all of the simple harmonic oscillators. Frequency and period are, once again, inverses of each other. So in this context, however, the period capital T is the time necessary for one wave to go by. And then we once again have this simple relationship. The two are inverses of each other, that is frequency and period, and here's the easiest way of visualizing that. For example, let's say that the frequency is 1 hertz, so one wave goes by per second. Therefore, what's the period, the time necessary for one wave to go by? It would just be 1 second. Let's say that the frequency is 2 hertz, so 2 waves go by per second. Therefore, what's the period? That is the time necessary for one wave to go by, ½ a second. So just like it is for uniform circular motion and also for simple harmonic motion, frequency and period are inverses of each other, once again, when talking about simple periodic waves. In terms of the definitions that we have here thus far, we can now write an expression for the speed v in terms of distance divided by time. So go all the way back to basic kinematics, for example, in chapter 2. Recall, of course, that speed is distance divided by time. A very useful distance to use, however, when describing simple periodic waves is the wavelength, and then therefore the time in the denominator of the expression would be the time necessary for one wave to go by. That, of course, would just be equal to the period. So speed as distance divided by time is wavelength divided by period. More times than not, however, you'll see this little expression not written in terms of the period, but instead written in terms of the frequency. So then therefore, equivalently, the speed is equal to the wavelength multiplied by the frequency. Keep in mind, of course, that essentially all of this is just a definition, nothing more than that, and we're using the same terms as we've already seen for uniform circular motion, simple harmonic motion, and now also simple periodic waves. Okay, now as I drew out this waveform here, pretty obviously we can then use a cosine curve, for example, to describe it. So let's now go ahead and use that cosine to begin to develop the function that we're looking for to eventually describe the propagation of this wave. Okay, so let me begin to draw out the cosine curve in the following way. Okay, so here's x and here's y. Once again, this represents a displacement from equilibrium. This represents the direction of propagation. And then let me just begin by drawing here a simple cosine curve like so. So in other words, if you took a picture of the spring that this wave has formed, this is literally what the spring would look like at this instant in time. Okay, from crest to crest here along the x-axis, that distance there is equal to the wavelength. And then the maximum disturbance from the equilibrium position, of course, is now the amplitude of the wave, A and negative A, like so. That's also the amplitude, of course, associated with all of the individual simple harmonic oscillators as they undergo simple harmonic motion. So then therefore, right off the bat at this time, and by the way, we're going to set this time t equal to 0 here for purposes of writing this down. Right off the bat, we can begin to write down this function in the following way. A cosine of something. So now, what is the argument here of the cosine function when describing what this picture looks like? Well, let's make a comparison between what we're doing here for a simple periodic wave and what we already know from earlier for simple harmonic motion. So recall the following kinematics equation that described the simple harmonic oscillator. Position as a function of time was A cosine omega t. And then recall how we graphed out this function as a function of time. When graphing the position of an oscillator as a function of time, we graphed out a cosine curve like so, where this right here is the period, the time necessary for one oscillation to occur. And then here and here, of course, was the amplitude position of A and minus A. And then the angular frequency omega, basically what the purpose of it is mathematically, is to turn a time into an angle. We do so by writing the angular frequency, recall, as 2 pi divided by a period. So now compare the argument of this cosine to what we're going to describe on the top board now for the argument of this cosine that's describing this wave. First of all, this cosine here is not a function of x, it's instead a function of time t. However, on the top board, when talking about a simple periodic wave, obviously the cosine is going to be a function of x. And then we're going to have here some number that mathematically is similar to omega. Once again, omega, the angular frequency, basically what it does is it turns here a time into an angle. On the top board, the number that's going to go in front of the x, it's referred to, by the way, as a small k. This right here turns a distance into an angle. Instead of 2 pi divided by the period, small k is equal to 2 pi divided by the wavelength, lambda. This distance here along the x-axis, which is mathematically analogous to this period here along the time axis. This new quantity here, referred to once again as k, it has nothing to do with a spring constant, by the way. It's referred to as the wave number. This is a new quantity for us, so let's go ahead and check the units. The units of the wave number k are radians per meter. Like so, as opposed to omega, the angular frequency, which was radians per second. But mathematically, the purpose of the wave number k is essentially to take a distance and turn it into an angle, such that we can describe it on the diagram. Now, this only describes what happens at this instant in time. A little bit later on in the next video, we'll see what happens as time evolves and the wave propagates. But before we get to that point, let's go ahead and use this function here with a simple example problem. Go ahead and copy this problem down into your notes while I now read it to you here. Okay, a wave function is given by the following. Let me go ahead and write this down. For cosine of pi over 4x in terms of meters at times t is equal to 0. Okay, what is the wavelength? Graph the function, and where is the position y equal to positive 1 meter? So as we begin to approach this problem, you'll see that it's mathematically similar to some of the basic problems that we looked at when talking about the kinematics of simple harmonic motion. Mathematically, there's not much difference between the two. Okay, now let's go ahead and identify everything in the function that we have here. Okay, first of all, the amplitude is 4 meters. That's obviously the coefficient here in front of the cosine. And now here in front of x, we have this new number, the wave number, which is pi over 4 radians per meter. And then from this value, we can immediately calculate what the wavelength lambda is equal to. So k is 2 pi divided by lambda. If you cross multiply here, lambda is equal to 2 pi divided by k. So then therefore it's 2 pi divided by pi over 4, which ends up being 8 meters. So it's a really big wave here. We're working with easy numbers in this example. Okay, and then in part B, we just merely graph out the function. And of course, it's just this graph. But let's go ahead and label things here appropriately for the example that we have. So this is x in terms of meters. This is y in terms of meters. What we customarily graph out here, at least initially, is 1 full wavelength. So then therefore, this distance right here along the x-axis is 8 meters. Here and here, the amplitude positions of 4 and minus 4, respectively. And then lastly, for part C of the problem, it asks now where is y equal to positive 1 meter. Here's what the question is asking. Where along the x-axis is the function itself equal to positive 1 meter? That is here and here. Notice that this occurs twice per wavelength. We're asked to calculate those two values of x, that is here and here. We'll do so by just taking the function, setting it equal to 1 in our example, and then in radian mode on our calculator, just solving for x. This is obviously very similar to solving for time, for example, as we did back in SHO kinematics situations. Okay, let me go ahead and do some erasing here. Let's go ahead and set the function equal to 1. And now let's go ahead and just solve for x. So divide by 4 to the other side, take the inverse cosine of both sides, like so. And then in radian mode on my calculator, I now have to solve for x. So let's go ahead and check the mode on my calculator and make sure it's in radians. And now let me go ahead and do here the left-hand side. So inverse cosine of 1/4, I'll write this down so you can check this later on as you calculate. It's about 1.32 or so, like so. And now I'll go ahead and cross multiply the 4 and the pi to solve for x. So multiply by 4, divide by pi, And the first value of x that I'm finding here, call it x1, is about 1.68 or so meters. That's pretty obviously this point here on my diagram. And then by symmetry, I can go ahead and find the second point here, just call it x2, by taking the 1.68 meters and subtracting it from 8. So then therefore by symmetry, we can now say that x2 is equal to 8 minus 1.68. Let me go ahead and do the math here carefully, and that comes out to be 6.32 meters, like so. So describing what happens with this simple periodic wave at this instant in time so far is rather straightforward. In the next video, we'll begin to explore what happens as the wave propagates with time.